For lesson 3.5, we will discuss the rank of a matrix and solutions of systems of linear equations. So first, we will discuss the rank of a matrix. So we have for an m by n matrix, the n tuples corresponding to the rows of A are called the row vectors of A. That is, if we have this matrix A, then the row vectors of A are the following. Okay, and also the columns of A are called the column vectors of A. So again, given this A, so the column vectors of A are this. Now let us have the definitions of row space and column space. So let A be an m by n matrix. So we have the row space of A is the subspace of Rn, n is the number of columns of the matrix A, spanned by the row vectors of A. Again, the row space of A is the subspace of Rn spanned by the row vectors of A. And similarly, the column space of A is the subspace of Rm. M is the number of rows of A spanned by the column vectors of A. Now, this next theorem tells us that row equivalent matrices have the same row space. So if an m by n matrix A is row equivalent to an m by n matrix B. So recall that two matrices are row equivalent when one can be obtained from the other by elementary row operations. So again, if an m by n matrix A is row equivalent to an m by n matrix B, then the row space of A is equal to the row space of B. Next, we have this theorem about the basis for the row space of a matrix. This states that if a matrix A is row equivalent to a matrix B in row echelon form, then the non-zero row vectors of B form a basis for the row space of A. So to make this clear, let us have these examples. So find the basis for the row space of A. So by applying elementary row operations to this matrix, we will obtain this row echelon form. We have this. You can verify, use elementary row operations. So we have this row echelon form corresponding to this matrix. So let us name these rows as W sub 1, W sub 2, and W sub 3. So by the above theorem, these non-zero rows of B are non-zero rows of B, W sub 1, W sub 2, and W sub 3 form a basis for the row space of A. Again, what we are looking for is that after you you write this given matrix into row echelon form, you look at the non-zero rows of the row echelon form. Then those non-zero rows will form a basis for the row space of the given matrix A. Another example, find a basis for the subspace of R3 spanned by the given set S. So we name these vectors as V sub 1, V sub 2, and V sub 3. We can use V sub 1, V sub 2, and V sub 3 to form the rows of a matrix A. So we have, and then we can use the technique we used in the previous example, that is, we will write A in row echelon form. So we have this one. Again, you can verify that. So the non-zero rows of B are these vectors, W sub 1 and W sub 2, form a basis for the row space of A. So W sub 1 and W sub 2 form a basis for the subspace spanned by S. Now this time, let us find the basis for the column space of matrix A. Note that the column space of A is equal to the row space of the transpose of A. So we write the transpose of A and we get this. Okay, so recall the transpose of a matrix. And then we will apply the same technique as in the previous examples. We will write this in row echelon form. So we have this. Let us name these rows as W sub 1, W sub 2, and W sub 3. So these non-zero rows form a basis for the row space of A transpose. And this is equivalent to saying that the column vectors, we have this, form a basis for the column space of A. So in here, we just write the non-zero rows we got into this as columns or the transpose of those row vectors. So we have now the basis for the column space of A. Now let us show another way to solve this problem or find the basis for the column space of the matrix A. So we see that this matrix A is row equivalent to this from example 1. Note that the row operations can change the column space of a matrix, but they do not change the dependency relationships among the columns. Observe that column 3 of matrix B, so this vector B sub 3, can be expressed as negative 2 times B sub 1 plus B sub 2. Again, so we multiply this by negative 2 plus this equal to this 1, multiply by negative 2 plus this equals 1. So your B sub 3 is equal to negative 2 B sub 1 plus B sub 2. And so, the corresponding vectors of A will also have this relationship. So we say that A sub 3 is equal to negative 2 of A sub 1 plus A sub 2. Also, you can check that the columns B sub 1, B sub 2, and B sub 4 can be of matrix B are linearly independent, and so are the corresponding columns of matrix A. Therefore, the corresponding columns of A, which are the columns A sub 1, A sub 2, and A sub 4, form a basis for the column space of A. We have the following column vectors. Next, so this theorem tells us that row and column spaces have equal dimensions. So if A is an m by n matrix, then the row space and column space of A have the same dimension. You can observe this in examples 1 and 3, where both bases for the row space and column space of matrix A contain 3 vectors. Please recall that the dimension is the number of vectors in a basis of space, vector space. So now we can finally define the rank of a matrix. The dimension of the row or column space, since they have equal dimensions. The dimension of the row or column space of a matrix A is called the rank of A and is denoted by this. Let us have an example in finding the rank of a matrix. Find the rank of a matrix, of the matrix A, given this. We will apply elementary row operations to obtain the row echelon form of this matrix. We name it as matrix B, the row echelon form equivalent to A. Because B has 3 non-zero rows, so these 3 non-zero rows form a basis for the row space of A. And so the rank of A is 3. Next, we discuss the null space of a matrix. If A is an m by n matrix, then the set of all solutions of the homogeneous system of linear equations Ax equals the zero vector is a subspace of Rn called the null space of A and is denoted by this. So we have the null space of A is the set of those vectors x, element of Rn, such that Ax is equal to 0. Okay, so these are the solutions to this homogeneous system of linear equations. The dimension of the null space of A is called the nullity of A. So again, take note of the term. We have the null space of A, and the dimension of this null space of A is called the nullity of A. Example, find the null space of the matrix, the given matrix and its nullity. So we have this matrix A. So we want to find the solution to the homogeneous system or homogeneous equation. We have Ax equals 0. We have the Ax equals 0 vector. So to do this, we may rewrite A first into reduced row echelon form. So A is, we have 1, 2, negative 2, 1, 3, 6, negative 5, 4, 1, 2, 0, 3. Okay, so let us apply elementary row operations. So we will make these two entries here 0. So recall, we have to make the 0, we can multiply row 1 by negative 3 and then add to row 2 to get new row 2. This is 0 multiplied by negative 3, so plus 6, that's 0. Multiply this by negative 3, so that's 6 minus 5, so that's 1. Then also 1. And then multiply this by negative 1 and then add to row 3 to get new row 3. So we have 0, 0, 2, and then positive 2. Okay, and then continue. We will make this entry here 0. So we have 1, 2, negative 2, 1, 0, 0, 1, 1, 0. We can multiply this by negative 2 and then add to row 3. So that means this becomes 0, negative 2, and then this becomes 0 also. Okay, and then we want the reduced row echelon form. So it implies that we can make this above this leading one, we can make this 0. So, okay, we can multiply this by positive 2 and then we add to row 1. So we have 1, 2, 0. We multiply this by positive 2 plus 1, so that is 3. Okay, so this is the reduced row echelon form equivalent to our given matrix A. Now from here, so we have the homogeneous system, so we can say that 1, 2, 0, 3, 0 multiplied by, we have x sub 1, x sub 2, x sub 3, x sub 4. We have 4 columns, so we have, this is 3 by 4, so we have 4 by 1 equal to 0, 0, 0. Okay, and from here, we get now the, linear system x sub 1 plus 2x sub 2 plus 3x sub 4 equals 0, and we have x sub 3 plus x sub 4 equals 0. So observe that we have two free variables. So we have x sub 4 and x sub 2. Okay, so we will let x sub 2 equals s and x sub 4 equals t, where s and t are any real numbers. So this implies that by substituting this x sub 4 or t here, so we have x sub 3 is equal to negative t, and x sub 1 is equal to, substitute s here and t here. So we have therefore negative 2s minus 3t. Thus we have the null space of A is equal to the set containing the vectors of the form negative 2s minus 3t, that's x sub 1, and then s, and then negative t, and we have t, such that s and t are real numbers. So next, let us find the nullity of A. So note that the solution vector x can be expressed as this. So by separating those with s and with t, so and factoring out s, so we have this one. So a basis for the null space of A consists of the vectors. We have this. Thus, the dimension of the null space of A is 2, and so the nullity of A is 2. Next, we have this theorem on the dimension of the solution space. If A is an m by n matrix of rank R, then the dimension of the solution space of Ax equals 0 is n minus R. That is, n, which is the number of columns of the matrix A, is equal to rank of A plus the nullity of A. Again, the rank is the number of vectors in a basis for the row space of A, and the nullity of A is the dimension of the null space of A. Now let us consider this next example. Let the column vectors of the matrix A be denoted by A sub 1, A sub 2, A sub 3, A sub 4, and A sub 5. Let us first find the rank of A and nullity of A. Again, to find the rank of A, we will write A in row echelon form, and then we get the number of non-zero vectors of the row echelon form. So let us write A first. Have 1, 0, negative 2, 1, 0, 0, negative 1, negative 3, 1, 3, negative 2, negative 1, 1, negative 1, 3, 0, 3, 9, 0, negative 12. Okay, so again, we want a row echelon form equivalent to this matrix. So we'll apply elementary row operations. So this implies, so let us make this 0 first. So we have 1, 0, negative 2, 1, 0, 0, negative 1, negative 3, 1, 3. Then we multiply row 1 by negative 2, no, that's 2 rather. So multiply by 2, and then we add to row 3. So we have 0, negative 1, negative 4, so that's negative 3. And then we have 2, so that's 1. And then we have 3. Then we have 0, 3, 9, 0, negative 12. Okay. And then we have here so we can make this positive 1 here, so that we will have a leading 1 on the second row. So that's, we multiply by -1, so that's 3, -1, -3, 0, -1, -3, and then 1, 3, 0, 3, 9, 0, -12. Okay, and then continue, we have, okay, so this time we can make these two entries here 0, so we add these two rows, row 2 and row 3. So notice they have opposite signs but with equal values or absolute values. So we have here 0, 0, 0, 0. And then we can multiply row 2 by -3 and then add to row 4. So that's 0, 0, that's multiplied by -3, so that's 3, and then multiply by -3, so that's -3. Okay, and then next, we can interchange these two so that we will have the 0 row on the bottom. So, and also at the same time, we can make this as a leading one. So we will have 1, 0, -2, 1, 0, 3, -1, -3. Again, so we multiply that one by 1/3. So we have 0, 0, 1, -1, and then we write down the 0 row. So we have now the row echelon form equivalent to the given matrix. So these non-zero rows or non-zero vectors form a basis for the row space of A. And so the rank of A is, so since we have 3 non-zero rows, so the rank of A is 3. Okay, and then now for the nullity of A, we can apply the previous theorem, that is n is equal to rank of A plus nullity of A. So the number of columns of the given matrix equals the rank of A plus the nullity of A. So this implies that nullity of A is equal to n minus rank of A, which is equal to n. We have the number of columns 1, 2, 3, 4, 5. So we have 5 minus rank of A is 3, so that is equal to 2. So the nullity of A is 2. Now next problem is we have find a subset of the column vectors of A that forms the basis for the column space of A. So we can further apply elementary row operations to this matrix so that we can obtain the reduced row echelon form. So that is, we have, this is a leading one, so we want the entries below and above it to be 0, so we will make this to 0. So first, to make this 0, we can multiply row 3 by -1 and then add to row 1. Okay, so we have here 1, 0, -2, 0. We multiply this by -1 and then add to that, so that is 1. And then to make this 0, we can add the two rows, row 3 and row 2. So we have 0, 1, 3, 0, and then we have -4. Then 0, 0, 0, 1, -1, 0, 0. Okay, so we have now the reduced row echelon form corresponding to the given matrix A. Now let us name this as matrix B. Now observe that in matrix B, the first and the second columns are linearly independent because one is not a multiple of the other. A scalar multiple of the other. Okay, and then, however, the third column, or let's say, so let us name this as B sub 1, B sub 2, B sub 3, B sub 4, and B sub 5. So the third column, B sub 3, is have equal to negative 2 b sub 1 plus 3 b sub 2. Okay, so we have again our column 3 is equal to, we multiply this by negative 2 and then times 3, so that's negative 2 multiplied by negative 2 times 3, so that is the product of negative 2 b sub 1 plus 3 b sub 2 is equal to b sub 3. Also, columns 1, 2, and 3 are linearly independent. Sorry, that's columns 1, 2, and 4, not 3. Columns 1, 2, and 4 are linearly independent. However, notice also that your b sub 5, or the fifth column, is equal to b sub 1 minus 4 b sub 2 minus b sub 4. Okay, so we have 1, negative 4, and negative 1. So again, b sub 1, b sub 2, and b sub 4 are linearly independent. Then, so again, row operations will not change the relationship between the columns of this and the columns of this. So if these three are linearly independent, this B1, B2, and B4, then so are the corresponding columns of A. So this is A sub 1, A sub 2, A sub 3, A sub 4, and A sub 5. Again, we say since these two are linearly independent, these three are linearly independent, then so are the corresponding columns of A. So we say that A1, which is equal to 1, 0, negative 2, 0. A2, which is equal to 0, negative 1, negative 1, 3. And A sub 4, which is equal to 1, 1, negative 1, 0, form a basis for the column space of A. Next, we have, if possible, write the third column of A as linear combination of the first two columns. So from here, we see that b sub 3 is equal to negative 2 b sub 1 plus 3 b sub 2. Now again, since the row operations doesn't change the relationship among columns, so we can conclude also that a sub 3 is equal to negative 2a sub 1 plus 3a sub 2. Okay, you can verify that. You can check that negative 2 times this plus 3 times this will be equal to a sub 3. Now let us have the theorem on solutions of systems of linear equations. If x sub b is a particular solution of the non-homogeneous system ax equals b, then every solution of this system can be written in the form x equals x sub b plus x sub h, where x sub h is a solution of the corresponding homogeneous system ax equals 0. Example, or for the proof, we have the proof first. So let x be any solution to this non-homogeneous system, AX equals B. Since we have A times X minus X sub P is just equal to, you can multiply the matrix here. So we have AX minus AX sub P. Since this is equal to B, and since X sub P is also a particular solution to this non-homogeneous system, so AX sub P is equal to B also. So B minus B is equal to 0. So we have here A times X minus X sub P equals 0. Then we say that X minus X sub P is a solution to the homogeneous system AX equals 0. And by letting X sub H equal to this solution, then you will have transpose this on the other side. So you can have X equals X sub P plus X sub H. Now for the example, find the set of all solution vectors of the system of linear equations. That is, we have this. Okay, so we have 3 equations and 4 unknowns. So we first write the augmented matrix corresponding to this linear system. And again, we apply elementary row operations. We can obtain its reduced row echelon form. So we have that. You can verify that again. So for the linear system corresponding to this reduced row echelon form, we have this one. Now observe that we have 2 free variables because we have 2 unknowns in two equations but 4 unknowns. So we have 2 free variables. So we have x sub 4 and x sub 3. So we will let x sub 3 equals s and t x sub 4 equals t, where s and t are real numbers. Then we can write a representative solution vector of ax equals b as, we have that. Okay, so we solve using this linear system. We substitute s to x sub 3 and t to x sub 4. So you will get x sub 2 as negative s plus 3t minus 7. Also, we substitute here the s and the t. So you will get x sub 1 as 2s minus t plus 5. Okay, and then we just write down for x sub 3, instead of s, we just write down 0t plus 0. And also for x sub 4. Now, this vector can be expressed as, we have that, separating those with s, with t, and with the constant. So, factoring out also s and t. So, we have this. So that we can express the solution as s times, we let this as u sub 1 plus t times, we let this as u sub 2 plus x sub p. Note that x sub p is a particular solution vector of ax equals b. Okay, so if we let this to 0, so this is a particular solution of the non-homogeneous system ax equals b, and x sub h is equal to this 2. This represents an arbitrary vector in the solution space of the ax equals 0. Next, we have this. We have a theorem on the consistency of linear system. So the system of linear equations ax equals b is consistent if and only if b is in the column space of A. And now we have the summary of equivalent conditions for square matrices. So this summary represents several major results that involves matrices, determinants, vector spaces, and systems of linear equations. We have, if A is an n by n matrix, then the following conditions are equivalent. A is invertible. Ax equals b has a unique solution for any n by 1 matrix B. Ax equals 0 has the trivial solution, so we have the 0 vector. And A is row equivalent to the identity matrix of order n, and the determinant of A is non-zero. The rank of A is equal to n. The n row vectors of A are linearly independent. And lastly, the n column vectors of A are linearly independent. Okay, so again, note that if any of these statements is true, then the other statements is also true. And that's the end of our discussion for chapter 3.